In this class, let us discuss CE amplifier and its operating point as well as load line concept. So in this circuit, here we are having this is the CE amplifier connected. So with VBB base voltage and VCC collector voltage. So here this VCC normally we take it as variable and VBB also we take it as variable to get the output characteristics of transistor. So first let us analyze the circuit. So when you take input loop equation for the circuit, so in the input loop equation if you take KVL in this way, so here VBB minus, so here the current in the base is IB, so minus IB into RB, and if you observe this is the voltage across base emitter, so normally we call it as VBE base emitter junction. So here this voltage is minus VBE is equal to 0. So from this we can understand IB is equal to, so if you take IB, so this is VBB minus VBE divided by RB. So this is the way we can find the IB value. So VBE is the supply voltage we are applying and VBE is the constant voltage. Observe when you forward bias, so PN junction diode, observe this transistor symbol carefully. So this is the arrow direction. So here it will be P type semiconductor and this is N type semiconductor and this is also N type. This is also, this is NPN transistor. This NPN transistor P2N junction, P2N we have to forward bias it. So when you forward bias this junction, the voltage across the PN junction diode will be always 0.7. So normally this VBE will be 0.7 volts. So here this VBE on. So when you switch on it, VBE on will be equal to 0.7 volts. And here RB, VBB is I am taking as variable. RB is the resistance that is constant. So by changing the VB, we will get different values of IB. And then similarly, when you take output loop equation here, so in this output loop equation, VCC, if you start output loop equation like this, so this is VCC minus IC into RC, the voltage drop across the RC, and from here to here, this is collector as well as this is emitter. So normally we take it as VCE. This is voltage across the collector to emitter. So minus VCE we will take. So is equal to 0. This is ground. So from this, if you observe, VCC is equal to VCC minus VCE is equal to IC RC. So here by changing the value of VCC, we can get different values of IC as well as VCE. So we can determine the value of IC and VCC for different values of VCC, and we can able to draw a graph like this. So this graph is between IC versus VCE. That means output current here. IC is nothing but collector current, that is nothing but output current, and VCE is the output voltage or output voltage across the collector emitter. So we are taking the graph between output current and output voltage. So we call it as output characteristics. So here we can draw this graph for different values of IB. So first we will take, I am taking IB is equal to 0 initially, and we will get a graph like this. And when you take IB, if you increase IB by further, that means by applying VB, observe this VB, by changing the voltage VBB, we will get different values of IB here. So for different values of IB, every time I will change VCC and then I will get different values of IC as well as VCE. We can plot this graph between IC and VCE for different values of IB as well as VCC. So then you will get a graph like this. In this graph, whenever you are operating a transistor, in the transistor data sheets, normally you will have maximum operating regions. So this transistor will have maximum operating collector current, that is IC max will be there, as well as maximum collector to emitter voltage will be there, as well as maximum power dissipation of transistor will be there. So these specifications will be given in the data sheet of transistor. So these regions will be given by the will be defined in the transistor data sheet. Now here if you observe, we should not operate the transistor beyond this maximum current, beyond this maximum voltage. So the power is nothing but product of voltage and current. So this is the curve we can use for maximum power dissipation. So we should use the transistor within this region only. And if you observe one more point, that when the VCE is very low, when the VCE voltage across the collector and emitter is very low, transistor will operate in the saturation region. So normally that means when Vc is very low, during this region the transistor is in saturation. And when IB is equal to 0, that means both junctions are reverse biased, the transistor will be in the cutoff region. So here the transistor will be cut off, here transistor is in saturation. So only this part we use for active region. So this active region will be used for amplification purpose. So this is the active region we use. This is the output characteristics of transistor. Now here we need to define the operating point of transistor. The operating point of transistor is nothing but at which we can operate the transistor without getting distorted output. That means if you observe the circuit carefully, so here I am taking different values. So from this equation if you observe, so here the variables are Vc is a one variable and Ic is one variable. Let us take Vc is equal to 0. When you take Vc is equal to 0, that implies, so what is the value of Ic now? Ic is equal to Vcc by Rc. This is the one value we are getting. So here when Vc, so let us consider the graph. Let us consider graph here. So here when Vc is equal to 0, so this Vc is equal to 0, at that point Ic is equal to Vcc by Rc. This is the maximum Ic here. And in the same way, when you take another from the same one, if you take Ic is equal to 0, when you take Ic is equal to 0 here, so when you take Ic is equal to 0, this Vce will become equal to Vcc. So here consider this graph. This is the Vcc axis. So when Ic is 0, correspondingly this output Vc is nothing but Vcc. So when you join these 2 points, we will get the load line. We call it as DC load line of the transistor, and slope of this load line will be equal to minus 1 by Rc, because when you see this equation, so if you write this equation in terms of y is equal to mx plus c, so here I am taking the y axis is Ic, so Ic is equal to minus Vce by Rc plus Vcc by Rc. So if you observe this equation carefully, so this is the, so when you compare y axis is Ic, x axis is Vce, so this m is nothing but this is the m. So this is the slope of the voltage, minus 1 by Rc. So minus 1 by Rc is the slope you are going to get in this, for this load line. Now what is the advantage of load line? Where you are drawing the load line? So this load line will give, from this load line we can understand where we can operate the transistor in this region. So from this load line, so this load line is intersecting with one of the output characteristics. So it is intersecting at this point with IB is equal to 0 with another IB. So when you increase the IB, let us take IB1, it is intersecting here, IB2 here, IB3, IB4, IB5, IB6. So let us consider you are operating the transistor at IB1. So when you take, so at this point you are operating the transistor. So when you are operating the transistor at this point, so if you take output swing, so here whenever the swing crosses VCE, it gets distorted. So when you take maximum signal, whenever it is crossing VCE, this output portion will be distorted. Similarly, when you consider the operating point exactly at this point, if you take operating point early here, so whenever the transistor is crossing the load line, again whenever it is crossing the VC is 0, so it is negative portion will be distorted. So where you have to consider the operating point. So this operating point always you have to take in the middle of the load line. So let us consider at this point. So if you take operating point exactly in this place, so what happens here is, so this will output can have a maximum swing. So now in this case the output will have maximum swing. So we can have maximum swing up to here to here. So normally we always consider VCE will have maximum swing when you take in the middle of the load line. So always we define the operating point in the middle of the load line. So this part is called as, this is VCE Q. Q means operating point, and here also this corresponding, this is IC Q. So normally we call this part, that is VCEQ comma ICQ. This point is called as operating point for the transistor. So when you choose the operating point near to cutoff, the positive portion will be clipped off. When you take near to saturation, negative portion will be clipped off. So normally we use we keep transistor in the active region only. So we'll take in the middle of the active region. So we normally will take in the middle of the load line. So this will give maximum swing for the transistor. So observe, this is VCE I am drawing, this is VCE. So VCE will have the highest swing sinusoidal waveform if you take in the middle of the load line. So this is about finding the operating point and the importance of load line. So load line we can get by from the output characteristics. Just take the output equation, write output equation in terms of y is equal to mx plus c. So this equation gives the equation for load line. So by taking different value, when IC is equal to 0 and VC is 0 and IC is equal to 0, we will get 2 points. By connecting these 2 points, we will get the load line, and the middle of the load line we will always take the as operating point. So what is the use if you use exactly if you operate transistor exactly at operating point is, you will get the maximum swing at output without any distortion. That is the purpose of amplification. So when you want to amplify a signal, the output should be in the same waveform with a increased power or increased voltage gain. Voltage gain should be there as well as current gain should be there, but without any distortion. So we keep operating point in the middle of the load line.